So we're on page 3 of your new booklet, Energy. Sorry. Just write on a piece of paper and copy it. Okay, so we're going to come across a few new equations today. Okay, so it's sort of like thrown at you, quite a few of them at the same time. The first one is probably the most basic of the energy equations, and it's called work done. Okay, so basically if you push anything, if you apply a force to anything, so you say you push something along for a certain distance, you are exerting some energy on that thing that you are pushing. Okay, so say you were pushing a box along the table, then the energy that you're applying is related to how much force you're giving it. Obviously, if you the more force, the more energy, but also how far you're pushing it. Okay, so that is what work done is. The work done is the force that you apply to something times by the distance that it travels. So when a locomotive pulls a train or a crane lifts a load, they have to exert a force. This force causes movement, and energy is then transferred from one form into another. So when energy is transferred from one form to another, we say that work is done. So again, so if you're pushing something across your desk, okay, then if it's stationary, if it's still at first, and then you're pushing it, then it's gaining kinetic energy, isn't it? Okay. Or if you're lifting something, okay, you're applying a force, you're applying a lifting force over a certain distance, the height. Yeah. So it's going from kinetic energy and gaining potential energy. Okay. So when energy is transferred from one form to another, we say work is done. And the amount of work done depends on the force used and the distance moved in the direction of the force. So our first equation is this one here. So it's capital E with a little W next to it for work done equals force times distance. So work done, and that's an energy, so it's in joules, equals force in newtons times by distance in meters. The only difficult thing about this is making sure you've got the correct units. So if you're given anything in centimeters or kilonewtons, you need to change it into the original SI units. Okay. If you are a fan of triangles, then it's EW at the top. So, nice simple example. A man exerts a force of 120 newtons on a barrow and pushes it a distance of 50 meters. Calculate the work done by the man. So you can probably do this straight away without thinking about any working, but let's write down the working just to be for your notes. Okay, so the force that he exerts is 120 newtons. The distance is 50 meters. We want to know the work done, EW. So EW is force times distance, so 120 times by 50, which comes to 6,000 joules or 6 kilojoules. So relatively simple equation to use, just watch your units. A few people have been marking your tests, which we'll get back next week. We're not watching their units carefully enough, so we're throwing away marks. Okay. So that's the first question. Sorry, Tommy. I just keep it as joules. So then if you have to go on and use it in another equation, at least it's in joules then as well. But if you change it and you change it correctly, that's fine too. Right, so that's the first equation. Work done is force applied times by distance travelled or distance moved. So the next equation that we're going to come across is a special version of that equation, force times distance. and it is for our old favourite gravitational potential energy. So anything that's lifted up. So, okay, you can apply a force through a horizontal distance by pushing something along a desk. You can also apply a force through a vertical distance. So work done is the force that you're using to lift something times by the height, the distance that it's travelled upwards. Okay, so when an object is lifted vertically upwards, it gains gravitational potential energy. The gravitational potential energy gained is equal to the work done lifting the object. So it's equal to the force times by the distance. So, but instead of using d for distance, because it's being raised up, we tend to use h for height. Okay, so here is a diagram of a mass m being lifted through a height h. Okay, so it's been lifted up that height. It's been moved that distance, that height. So the force required to lift the mass at constant speed is equal to its weight. Because if you think about anything you're lifting up, you have to be able to apply the same as its weight downwards to be able to lift it up. So the force is equal to its weight, which is mass times gravitational field strength. And the distance moved by the mass is equal to the height. So d is the h. So instead of writing work done equals force times distance, we can say force is m times g times by the height. So gravitational potential energy is given by this equation, EP equals mgh, and that's your second equation today. So where EP is gravitational potential energy, joules, m is the mass in kilograms, g is the gravitational field strength, which is in newtons per kilogram, and h is the height in meters. Do you all remember mg, W equals mg from last year, hopefully? Yeah. So your potential energy would be different on different planets. Yeah, your potential energy is all dependent on G as well. Right, so we've got an example there. A crane exerts a steady force of 5,000 newtons while slowly lifting a large crate to a height of 4 meters. First of all, part A, how much work is done by the crane? So we know the equation work done is force times distance. And it's told us it's applied a steady force of 5,000 times by the distance, which in this case is the height of 4. And that's 20,000 joules. And B, favorite trick question, how much gravitational potential energy is gained by the crate? The same. So gravitational potential energy is just the work done. So it's the energy transferred. So gravitational GPE is the same as work done. So because the F is mg, so EP equals mg, put that in brackets, times by height, because we know that mg is just that force, so it's 5,000 times 4, so 20,000 joules. Everyone see where I got that from? Yes. So work done and gravitational potential energy are kind of the same equation, but in different formats. Yeah. Oh, 9.8. Yeah, that's a good point actually. Don't use, so in second year I think you use 10 for gravitational field strength. So in third year in National 5 you use 9.8 for gravitational field strength on Earth. So if you want to write that down, so G on Earth is 9.8 newtons per kilogram. Um, yeah, I believe it is in the data sheet at the start of any exams. However, you will remember it. Like, there's no way that you're going to forget that because you use it so often in the next sort of few topics that we do. So 9.8 on Earth. Unless, of course, the question tells you differently. So the question says use 10, you use 10. If it specifically says that in the question. Right. So that's two equations. We've got work done is force times distance. We've got gravitational potential energy is mass times g times height. The third one is kinetic energy. Now this is not sort of a version of work done, although you can still calculate it using work done. So kinetic energy, if a trolley is given a push along a bench, we know it gains kinetic energy. And the kinetic energy gained by the trolley, it's quite important, is equal to the work done on the trolley, assuming friction is negligible and there's no other energy lost. So basically, if I'm pushing this trolley along this desk, yeah, the amount of work that I put in is all transferred into kinetic energy at the end of it, unless there's any friction and some of it will be lost as heat and sound. But if we assume that friction is negligible, which we will do in the first few questions that we do, then you can assume that all the work done, so all the force times the distance that I've pushed a trolley, changes into kinetic energy. Okay. I think when some of the questions that you're going to do later, that will be important too. So kinetic energy is dependent on the mass and the speed of an object, because we know that the faster something is, the more kinetic energy it has. But also the mass is important in kinetic energy. The kinetic energy of an object of mass m moving at speed v is given by Ek for kinetic energy equals half mv squared, where Ek is the kinetic energy in joules, half is just a number, m is the mass in kilograms, and v is the speed in meters per second. Remember, ms to the minus 1 is just another way of writing. So it's not, you don't need to put minus 1 into your calculator or anything like that. How come the speed is squared? Because basically that's how it's dependent on speed. So it's not directly dependent, so it's not a direct relationship with speed. Actually, as kinetic energy increases, the speed is squared. So actually the speed increases more with energy. So if you have more energy, the speed's actually squared the speed. You see what I mean? The mass doesn't half. It's just that's just a constant that's in there that works with the equation. So basically, what somebody did was they did an experiment, and they were measuring the kinetic energy of something. And what they did was they would change the mass. So as the mass increased, the kinetic energy increased, and that's like a linear. That's like as one goes up, the other goes up. But they found when they were doing the experiment, as with the speed, and they measured the speed and changed kinetic energy, and they found that as kinetic energy went up, speed squared. Yeah. So it's just basically it all comes from experiments. So the half is just a number that's in the equation as well. It doesn't actually affect any of the others. Good question. Right. So a cricket ball of mass 0.8 kilograms is thrown at a speed of 20 meters per second. Calculate the kinetic energy of the ball. Okay. Now, this one, I can guarantee that one of you, or no, more than one of you, quite a few of you, in your lifetime doing physics, when you're doing the energy, you'll forget to square the speed. Okay, guarantee that's going to happen, probably in the test in this book of this booklet. Okay, so just be careful when you're doing these equations. So we've got a mass of 0.8 kilograms, got a speed of 20 meters per second, and we want to find the kinetic energy. So we go kinetic energy equals half mv squared. So it's half times by the mass, 0.8, times by the speed squared. And that should come to 160 joules. Okay. B asks, how fast would the ball have to travel for its kinetic energy to double? So I'd like you guys to have a go at that. So obviously, a double kinetic energy is going to be 160 times 2. So 320. So you know now the kinetic energy, but you don't know the speed. So you're trying to find the speed. So it's a bit of a rearrangement problem. So remember what to do, put all the numbers in first, work out as much as you can, then rearrange it. So have a go. No, the mass stays the same, yeah. So it's the same ball.